This has to start working. Is this working? Anyways, that's right. I am going to be beating Geometry Dash. It's an extreme demon. It's a huge jump from a hard demon, and I have 98% on it. By the way, I am using FPS bypass to get 120 frames per second. Also using accurate percentage and practice music hack, but that's all. Oh, one more thing. Let me just edit the title. By the way, massive. By the way, shout out to SciShow.
There's a good chance you know the cats and dogs on your block better than you know the trees and flowers. And hey, that makes sense. No judgment here. After all, plants don't greet you on the sidewalk, get in fights with raccoons, or sneak up on you when you're walking home in the dark. They keep a low profile. But really, plants are amazing. They give us food and oxygen, they decorate our homes, and they're also really fascinating organisms. We've talked about plants a ton on this channel and thought it was about time to compile some of our favorite episodes about them. Speaking of time, here's Hank to explain how plants can tell what time it is. Because, apparently that's something they can do.
Plants don't have brains. It's probably not news to anyone. Plants also don't have muscles or anything resembling a nervous system, and yet they can move. In some plants, this is actually pretty dramatic. Think Venus flytrap. But there are tons of plants that move more slowly, and they do it in time with the coming of day and night. So how do they move, and how do they know when to do it, all without a brain or any of that other stuff? Many plants, such as members of the legume and wood sorrel families, tuck their leaves in at night. We don't totally understand how this happens, and we have almost no idea why, but scientists have identified some of the players involved. The process of how plants tuck themselves in at night is called nyctinasty. Nastic movements are a plant's movement in response to a stimulus that doesn't occur in a particular direction. The leaves don't follow the moon or anything, they just droop. Temperature change plays a role in this response. The cooler night air can help signal the plant's reaction, and the warming sun in the morning does the opposite. But it gets quite a bit more sophisticated than that, involving not just temperature changes, but several different types of chemical reactions. One player in this process is a molecule called Phytochrome, which absorbs light. Phytochrome participates in a reversible chemical reaction, meaning it doesn't just react to form a product and then stop. Instead, it can switch back and forth between two different forms depending on the conditions. These two forms are called PR and PFR. Initially, Phytochrome takes the form of PR, so called because it absorbs red light, which there's more of during the day when the sun is out. As PR absorbs red light, however, it is converted into PFR, which absorbs far red light instead, basically the less intense wavelengths as the sun sets. Absorption of far red light causes PFR to convert back to PR. Some of it will change back over time in the absence of any light as well, which means that the phytochrome automatically cycles back and forth between forms depending on whether it's day or night. These changing forms of phytochrome are important in structures called called pulvini. A pulvinus is a region of bulbous tissue at the base of a leaf that acts as a flexible joint. It's like a plant elbow. When enough PFR is present in the pulvinus, the plant pumps water to a specific section of the joint. The change in water pressure within the cells, called turgor pressure, basically flexes the joint like a muscle, which bundles the leaves up for the night. When the chemical reaction reverses, the turgor pressure shifts back. Additional leaf chemicals called leaf-closing and leaf-opening substances also play a part in nighttime leaf opening and closing. There's a lot of variety in these chemicals, but the general idea of oscillating chemical reactions is similar. In the same way, many flowers open in the morning and close at night for reasons that are even more poorly understood. It might be to conserve a flower's scent, to protect their nectar, to keep pollen dry, or some other reason, but the mechanism might be similar. Petals, after all, are just a type of leaf. This isn't the only kind of day and night plant movement either. Many species actively follow the sun during the day in a process called heliotropism. Unlike nastic movements, tropisms are plant movements that are oriented in a specific direction. Heliotropism can help leaves get the most possible sunlight. Often, heliotropism in leaves is also controlled by turgor pressure in pulvini, if you wanted a lot of new terminology all in one sentence. So in this case, the leaves can move continuously to track the sun throughout the day rather than just opening and closing. And some flowers follow the sun too. It seems to have a few benefits, like providing a nice warm place for pollinators and helping the plant's seeds develop. But many heliotropic flowers have no pulvini. Young sunflowers instead turn to face the sun by growing their stem on one side at a time. It's not totally clear what chemicals the sunflowers use to sense sunlight, but the changes in stem growth appear to be governed by a hormone called auxin, which in this case tells certain parts of the plant to grow in response to light. The stem of the sunflower grows faster on the side that gets less light, thanks to a higher level of auxin activity on the shady side. That tilts the developing flower toward the sun. At night, in the absence of sunlight, sunflower stems reorient themselves to face east again, and in the morning, the light-directed growth process resumes. But sunflower stalks don't keep growing forever. Solar tracking only happens in young sunflowers. Once they're fully mature, the flowers face east and never move again. So now you know how to tell what direction things are if you're in the middle of a sunflower field. And you also know that plants don't need brains or nervous systems or muscles to respond to their environments, as long as they've got chemistry on their side. And they're more sophisticated about it than we think, able to keep track of time and act appropriately, which is pretty smart.
So plants know when the sun rises and sets. That means, in my part of the world, they know that the sun is starting to set earlier and things are cooling down. Around our office, we've started keeping the windows and doors shut to block out the winter chill. But if you're doing the same thing at home, things might start to feel a bit stuffy. So in place of that fresh air wafting in with the breeze, could you just keep a few houseplants to purify the air instead? Here's what the science says. It seems like every workplace has that one person who swears that the potted spider plant sitting on their desk has an almost magical ability to purify the air in the office. Are they actually onto something? There is evidence to show that plants can remove pollutants from indoor air, but a single potted plant probably won't go the distance. If you've heard that bringing plants into your home or office will improve your indoor air quality, you probably have a study conducted back in 1989 by NASA to thank for that. The goal was to test whether a variety of types of indoor plants could be used for air purification, both on Earth and in space. The plants were put into sealed containers and the air pumped full of chemicals including benzene and formaldehyde. Those chemicals fall under the broader umbrella of volatile organic compounds, or VOCs. Some VOCs are known to cause health issues like headaches or liver and kidney damage. And they're noteworthy as indoor pollutants because household products and building materials can give them off. The plants are kept under controlled conditions with plenty of light and water, and the air quality was measured over a 24-hour period. The study found the majority of plants